Okay, we're talking about how to avoid page faults by using good page placement algorithm. Here we will discuss how many friends are required for each process, and this problem actually depends on the hardware machines. Okay, uh, because different machine instructions may have different requirements. For example, in IBM 370, they may require up to 6 pages for a single SS move instructions, because this instruction may require 6 bytes, and this 6 byte may span 2 pages. Okay, and this SS move means they move a block of memory from one place to another place. So the source address and the destination address both may span 2 pages also. So to be able to execute this particular instruction, they may require up to 6 pages all in memory. So this particular instruction may be able to be executed. Okay, so this is the physical requirement or restriction by the machine itself. Okay, by machine instruction. Okay? So the minimum number of physical frames for each process depends on depends on the machine itself. Okay, so to allocate physical frames to process, usually we have two uh, category of allocation mechanism. One is fixed allocation. Okay, for example, you can use equal allocation. You assign each process same number of frames. For example, you divide the all physical frames available to the number of process, for example, n. Okay, and if this number is larger than the minimum requirement uh, of the machines, then it's all right. Okay, the second physical allocation is that instead of divide the physical frame equally to process, may assign these physical frames to process based on their size. Okay, so the assignment will be depends on the proportional size of this process. As long as every process get enough physical frame, which is the larger than the minimum requirement, then it's all right. Okay. The second policy type of policy is priority allocation. It's proportional to the priorities. Okay, so actually the proportional to size is a weight of priority also. Okay, because the priority is the weight, the size of the process. Okay, but in general, priority usually it will not be direct related to the size of a process, usually related to the importance of the process. Okay, and for priority allocation mechanism, it may allow a process to select a replacement frame from a lower priority process if the low priority process um, has more page frames. Okay, uh, and so on. So, and this kind of replacement, sometimes we call it global replacement. Okay, instead of local replacement. Okay, and local replacement means a process only select those frames which is assigned to itself. Okay, global replacement means a process may select a replacement frame from other processes. Okay, so that depends on the candidate or the victim you selected to replace. Okay, if the victim came from your own friends, then it's local replacement. If the victim friend can be selected from other process, then it's a global replacement. Okay, so in general, the priority allocation usually will be associated with global replacement. Okay, so that's the design consideration. So when we design this page replacement mechanism and make the allocation or managing the physical frame number associated with each process, you need to consider these factors also. Okay. To make a process running smoothly without too much page faults, okay, not only we need to have a good page replacement algorithm, and we also need to assign the physical frame number is larger than the minimum requirement set by the physical machines. Okay, and also here we will discuss another important factors. We call it locality principles. Okay, that means in general, when a process is executed, usually they will refer to a set of memory. Okay, and this set of memory is currently referenced. We call it working set. Okay, and during the life cycle of a program execution, the working set is dynamically changed. Okay, from the also its size itself dynamic changed. Okay, depends on where the execution of this particular program is in which part of the code segments. Okay, and another set we call a resident set is the set of pages that is currently in physical memory. Okay, so you have two sets. One is the set of pages currently required to be referenced during the current execution. Okay, and the set of memory or set of pages which is currently holded in the physical memory we call resident set. So if a process is resident set always cover its working set, then you can imagine that the process can be running without too much page fault because or it currently required page are in memory, right? In the other hand, if the resident set did not cover the whole working set, the current working set, then the process will anticipate a lot of page fault because whenever you need a page which is not currently in the physical frame because of the resident set, or especially if the size of the resident set is less than the working set, okay, the size of the current working set, then you will anticipate a lot of page fault. Okay, so in general, this locality principle tell us that if we can measure or we can monitor the locality of a process life cycle, so we can have a good estimation of the working set, current working set, then it's possible we can always assign a good resident set which can cover its current working set. Okay, if a process can be maintained in this kind of situation, then this process, the page fault will not be too much. Okay, so in other hand, if the working set is not a subset of its resident set, then the process will require frequent page faults. Okay, and this kind of situation in general we call it flourishing. That means the process doing a lot of page fault to move in, move page in and out. Okay, to continue its process. Okay, and flourishing, the formal definition for flourishing is that a process is busy swapping page in and out. It did not doing actual work for the process. Okay, and this will lead to CPU utilization. The physical CPU, effective CPU will become low. In most cases, if the CPU utilization becomes low, operations usually take a strategy to increase or involve more process into the system, okay, try to boost the CPU utilization. But if the reason for the low CPU utilization is because too much page fault, then this increasing or increased number of process in the memory will make the situation even worse. Okay, so you generate more page faults because the reason for the low CPU utilization is CPU doing too much work in threshing. Okay, instead of waiting for some I/O or whatever. Okay, so to the auction set model or the is you proposed try to management to make the system make a process page 4 can be controlled in some portion, okay, in some reasonable frequency, so will not generate too much page 4 and lead to a threshing situation, okay. But because it's very difficult to estimate the current working state when a process is running, okay, unless you have a good knowledge about a particular application, okay, and you make a lot of indication or inside the program itself. So whenever a program run into a particular set checkpoint, then the system will inform system that now the current working state need to be changed. It's changed, so you need to have more physical flag be assigned, and so on, whatever. So that's a possible way. Okay, you embed some messaging mechanism into the program. So whenever there's a big change of its working state, then the operating system will be informed and take proper operation to handle that. Okay. The register management problem is that you try to give every process a good size of a reasonable size of the physical memory, such that each resident set size of resident is always bigger than its the size column working set, okay, and so on. Okay, and to avoid create threshing or create many page faults. Okay. Another mechanism, instead of try to get or monitor the current working say and make a good resistance management, okay, for based on this estimation. Another approach is that instead of try to monitor this set, okay, we just use the page 4 frequency or page 4 rate as an indication, because that's the outcome. Okay, if you did not manage the resistance set properly, then you will generate a lot of page fault. Okay, and so the purpose is to make the page 4 rate in an acceptable level. Okay, so you can measure the according to history to set up two threshold. One is for low threshold, one is as upper bound, one is as a low bound, okay, of the actual page 4 rate. Okay, so and if a process has too much page 4, that means its page 4 rate is higher than upper bound, then you try to give this process more physical flags and to reduce its page 4 rate. Okay, and this assumption is that if a process will give more physical flag, then the page 4 rate should be reduced. Okay, that assumption is based on that if the replacement algorithm, page replacement, has not do not have this Benedict's anomaly, okay, as the FIFO allocation replacement algorithm, okay. If the replacement algorithm you used did not have this Benedict anomaly, then give a process more physical frame that will reduce its page fault rate. Okay, so as long as process page fault rate higher than upper bound, then you give it more physical frame. When a process anticipate too low of the page fault rate, okay, is too little page fault, then that means this process possibly contain too much physical frames. So we can decrease the number of physical frames assigned to this kind of process to increase its page fault rate a little bit, so the rate will in the middle of the low bound and the upper bound. Okay, so this page fault frequency mechanism is more typically used than the working set or resident set models, because we just check the outcome. Okay, if the page fault rate is in between of this upper bound and lower bound, then the system should be work fine. Okay, if any process is out of this bounds, then you do relative adjustment to make all the process behave. They have the page fault rate in the middle of this upper bound and lower bound. Okay.